For this problem, we're asked to come up with the linearized equations of motion for the 3-degree of freedom system that's shown here in the figure. It turns out that using the generalized coordinates of x1, x2, and theta shown in the picture, the Lagrange's equations of motion will be nonlinear, primarily due to the rotation angle of theta. We could derive Lagrange's equations and after the fact reduce it down to its linearized form, but what we want to do here is learn how to do it straight away from the kinetic energy and potential energy expressions without actually going through the formality of using Lagrange's equations. So what we have here, again, our generalized coordinates are x1, x2, and theta. In terms of names, what I'm going to do is let x1 be represented by q1 and x2 by q2, and theta will be q3. And I think that you can see by inspection that for equilibrium, all the q's will be equal to 0. So that's the state about which we want to linearize our equations. So let's write down T. T is going to be 1/2 mv squared. We see that v1 is just going to be equal to, the speed is going to be x1 dot. So this is x1 dot squared. It's going to be 1/2, and I'm sorry, this should be a mass of 2m. Then we have 1/2 mv2 squared, so that's going to be equal to x1 dot plus x2 dot quantity squared. And then for particle 3, what we will have is 1/2 m, and that will be x1 dot plus x2 dot plus L theta dot cosine. That's the I component. We square that. And the j component, L theta dot sine theta, that gets squared and added on to there. So just as a reminder, this is the speed of particle 3 squared. This is the speed squared of particle 2. And this is the speed squared of particle 1. What we will do is expand this out. Maybe I'll expand this out by itself. That's going to be, we have 3 terms that get squared. So it's going to be x1 dot squared plus 2x1 dot x2 dot plus x2 dot squared. So I'm really looking at that term there, squared. Add on to it 2 times L cosine theta, x1 dot plus x2 dot theta dot, and then we have an L squared theta dot squared cosine squared, and we'll have an L squared theta dot squared sine squared. So we have cosine squared plus sine squared. That will simplify down to a 1. So whenever we put together our terms, I guess maybe off to the side I'm going to explain that this is equal to x1 dot squared plus 2x1 dot x2 dot plus x2 dot squared. So now whenever I group together my terms, what is appearing in front of x1 dot squared is going to be a 3m. What is appearing in front of x2 dot squared is going to be a 2m. What is appearing in front of theta dot squared is 1/2 ml squared theta dot squared. What is appearing in front of the cross term of x1 dot x2 dot is 1/2 of 4m x1 dot x2 dot. The cross term of x1 dot and theta dot, that has a coefficient of 2ml cosine theta, x1 dot theta dot. And lastly, the cross term of 1/2 2ml cosine theta is also the coefficient in front of x2 dot theta dot. So again, all I've done here is expanded out the squares, grouped together the coefficients of the different terms of the x1 dot, x2 dot, and theta dot. Going back to our expression that this should be 1/2 the double sum over I and j of mij qi dot qj dot, with the understanding that mij and mji are the same. These coefficients are symmetrical. It's not difficult to see that this is what m11 is. This is m22. This is m33. This one, we know it's going to be the coefficients of m12 and m21. It's going to be added together. This will be the sum of m13 and m31. And this will be the sum of m23 and m32. That's just looking at the form of our double sum. And taking into account that the symmetry exists in these mass matrix coefficients, whenever I write down my m's, I know that this is equal to like 2m23, which is the same thing as m32. This will be equal to m12 times 2, or 2m21, either one of those. And same way for here. This is going to be 2m13 and the same thing as m31. Again, because of the symmetries for the m's. So the mass matrix M, those coefficients, I'm sorry, I'm saying this actually wrong. We're not talking about mass matrix yet, but just the inertia coefficients of lowercase m will be 3m, 2m, ml cosine, 2m, ml cosine, 2m, ml cosine, ml cosine, and ml squared. So this is what just comes out of our inertia coefficients. In order to write down our mass matrix, we take our inertia or mass coefficients and evaluate them at the equilibrium state, which we saw for this example is when theta is 0. So everywhere that there's a cosine theta, that becomes a 1. So 3m, 2m, ml, 2m, 2m, ml, 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 ml squared. And just by our observation, we force this to be a symmetric matrix there of M. We do the same kind of thing, although the process is a little bit different, for our potential energy function. We have the one spring, 1/2 k x1 squared. This is the L-shaped bar and ground, the spring that goes between those. Between the L-shaped bar and block 2, we have 1/2 k x2 squared. And then we have the gravitational potential of minus mgl cosine, where I drew my datum line passing through point A there, or I'm sorry, the pin joint there on block 2. The way we find our stiffness matrix coefficients is to take the mixed partials of U with respect to the Q's, and when we get through, we evaluate that at the equilibrium state, which in this case is Q equal to 0. So if we do that, we see that there are very few non-zero terms here because there's really no coupling in the stiffness among the 3 coordinates. We only get non-zero on diagonal terms. And so therefore our stiffness matrix, once we do this evaluation, is a diagonal matrix of K, K, MGL. For our damping matrix, being that we do have dissipation here, we got 2 dash pots, one between ground and the L-shaped bar, and one between particles 1 and 2. So we write down our Rayleigh dissipation function, 1/2 Cx1 dot squared plus 1/2 Cx2 dot squared. The damping coefficients are the mixed partials of the Rayleigh dissipation function with respect to the Q's, the Q dots, evaluated at the equilibrium state. So this says that our damping matrix C takes on this form. C, C, and a 0 on the diagonal, and zeros on the off diagonal. Again, this problem would have a nonlinear set of equations if you would use Lagrange's equations to derive those. And that is one path that you could take, is to derive those and then do the linearization after the fact. The approach that we have here is to do that right up front, take our kinetic energy, potential energy, and Rayleigh dissipation functions and directly write down M, C, and K.